Okay, we're going to talk about composition of compounds. So chemical formula actually gives us a lot of good information. We can combine the formula with the molar masses of the elements that are in that compound, and we can get relative quantities of each element. This can be expressed as a mass percent composition, or usually just called a mass percent of an element. So we use a lot of percentages in science, and so it's very helpful to have an idea about what exactly is a percentage. A percentage is the part that you're interested in divided by the whole thing, times 100. So, my oldest son's kindergarten class, 20 children, 15 of them were boys. So what percentage were boys? Well, you take the ones you're looking at, the ones you're interested in, the part, which would be 15 boys, you divide by the total number of children, 20 children, multiply by 100, and you get 75%. So when we do this with an element in a compound, we're looking at the mass of the element divided by the mass of the whole compound to get a percentage. So we can calculate this from two different sources. If we have the formula, we can calculate percent composition just from the formula, or sometimes we just have experimental data and we can calculate it from the data as well. So if we have the formula to find the percent of element X in the compound, here we don't have any masses given to us. The percent of X is going to be the same no matter what size sample you have. So we can calculate it from the formula, but it's helpful to have like an amount so we can get some actual masses. So we can just choose whatever amount we want. So we might as well choose something that makes things easier. So we choose 1 mole. So you choose 1 mole of the compound, you figure out what's the mass of your element in 1 mole of the compound, divide by the mass of 1 mole of the compound. That is the molar mass. Multiply by 100, and you're done. If you have experimental data, you're going to have masses. You're going to have a mass of element X. You might have a mass of the other elements, or a mass of the compound overall. You're going to take the mass of X divided by the mass of compound. If you don't have a mass of compound, then you have to take all the parts and add them together. If you calculate the mass percent for each element in a compound, they should add up to 100%. That might be a little bit off. You might end up with 101% or 99.5%, and that's due to rounding, and you shouldn't be concerned about that. So let's do an example here. Acetic acid is the active ingredient in vinegar. Calculate the mass percent composition of oxygen in acetic acid. So this is a problem where we're given the chemical formula. And there are no masses in this problem, but we can still calculate the mass percent. This is something where we need to use an equation, so it's helpful to write the equation first. We want percent oxygen, and so that's going to equal grams of oxygen per grams of the compound, C2H4O2, that's the whole thing, times 100 to give us a percentage. But we have no masses. So we're going to choose 1 mole. You could choose 3.5 metric tons, but why? Why make things hard? We're just going to choose 1 mole. Can we figure out the mass of 1 mole of acetic acid? Yeah, we just learned how to do that. That's the molar mass. So 1 mole of acetic acid, this C2H4O2. We're going to look at how many atoms of each element are in 1 molecule, and we're going to use the masses from the periodic table. So there are 2 carbons in the formula. That means in 1 mole there's 2 moles of carbon. So 2 times 12.01 and there are 4 hydrogens, so 4 times the molar mass of hydrogen, and 2 oxygens times the molar mass of oxygen. Remember this from Monday? Yeah. That's a good question. So I'm writing 16.0 for the mass of oxygen, and a lot of periodic tables will say 15.99994. Right? Those aren't exactly the same. Either one will give you the correct answer. It's a matter of precision. Ideally, you would use the most precise value you have. The periodic table that I've used for decades has all of the molar masses rounded to 4 significant figures. I have a lot of those memorized, and so like this problem, I don't even look at the periodic table, so I tend to just use 4 significant figures. Sometimes students want to round to 2 significant figures, and sometimes that comes out okay, and sometimes it doesn't. Now, obviously, if you rounded the mass of oxygen to 2 sig figs and just called it 16, that would be fine, but some of the other ones like chlorine, 35.45, that's like in the middle, and you round that off, and then you get problems. So it's okay to round your molar masses to 4 significant digits. Don't go any fewer than 4. It is also absolutely fine to use all the digits that are shown in whatever periodic table you're using. Okay, good question. So we can calculate this. And when you're calculating a molar mass, I would encourage you to always write this down as the bare minimum of showing your work. 2 times 12.01 plus 4 times 1.008 plus 2 times 16. So my calculator's giving me 60.052. Because I rounded my sig figs, this would have 4 significant figures. You don't ever end up with a bunch of extras because we're just adding. So what's the unit on that? It's grams. We're finding the mass of 1 mole of the acetic acid, and so the unit is grams. If we were finding the mass of 1 molecule, it would be atomic mass units. And you could do this problem that way as well. So that's my mass of 1 mole of acetic acid. So I can put that into my formula here. So that many grams. And then I need to know how many grams of oxygen were in that. I kind of already have the work done. This piece right here. In 1 mole, there are 2 moles of oxygen. So there are 32 grams of oxygen. So whatever element I'm finding the mass percent of, I just pull out the term for that element. In the formula, there are 2 oxygens, so 2 times 16. So that goes up here. And I multiply by 100. Look what happens with the units. I have grams in the numerator, grams in the denominator. Those are going to cancel out. The units should cancel when you do a percentage. And then you just end up with percent as the unit. So I've got 32 divided by 60.052 times 100. And I get a whole mess of numbers here. So I should have 4 sig figs because of how I rounded. So 53.28. I'm going to write down the next 2 digits. And then I'll go back and round this. 53.29% oxygen. Any questions? Yes?
So like I got 52.89 or 0.88%, but that's because of that different amount of sig figs that I used. So would that still be wrong?
Well, that seems kind of different. So what mass did you get for the whole compound?
60.0516.
Okay, and what did you get for the oxygen?
31.9988.
Hmm.
So I did just the 15.9994 times 2.
Yeah.
We got 31.9988.
Well, let me just check here because they should be closer than that.
Oh no, I did it again. Sorry. It's he gave me 53.2855.
Okay, that's better.
Okay. Sorry.
That's okay. That happens. Like I said, anytime you're doing a calculation, it's always a good idea if you care about the answer being right. And if you don't care about the answer being right, why are you even doing the problem? Right? It's always good to punch it through in your calculator twice because it's so easy to make a little mistake. I mean, I've been doing chemistry for longer than most of you have been alive, and I screw up on YouTube videos. I make some stupid calculation. Happens all the time. So you guys are going to screw up too. It's okay. Any other questions? We can also use the mass percent as a conversion factor. It will convert between mass of one element and mass of the entire compound. And so here we're going to think about percent in a different way. Percent literally is per 100. So it's how many per 100. In my son's kindergarten class, 75% boys. That means if you had 100 children, 75 would be boys, right? 75 per 100 children. There weren't 100 children, but that's the percentage. So we can take a percent by mass and turn it into a conversion factor very easily. So here's an example. We've got Freon 112. There's the formula. Here we're just given the percent composition of chlorine. You could calculate that, but they gave it to us. 69.58% chlorine. So that means 69.58 grams of chlorine per 100 grams of compound. Now, this isn't the only way to do it, but I think it's the most straightforward. So a percentage is that many per 100 of the whole thing. So let's do an example using this. So what mass in grams of iron 3 oxide contains 58.7 grams of iron? Iron 3 oxide is 69.94% iron by mass. Now we could figure out the formula and do the calculation a different way, but this is titled Using Mass Percent Composition as a Conversion Factor, so that's what we're going to do. So I'm looking here, and I do have some numbers, so I can write those numbers down as a starting point. So 58.7 grams of iron, and then I've got 69.94% iron. So I want to rewrite that percentage as a per 100. So that is the same as 69.94 grams of iron per 100 grams of the compound. Okay? Percent per 100. So this relates the mass of iron to the mass of the entire compound. Here I have the mass of iron. They're asking me for the mass of the compound. So this is my given thing, and my thing I'm trying to find, grams of iron 3 oxide. The percentage allows me to convert that in one step. So I start with my given quantity, 58.7 grams of iron. And I'm trying to find grams of iron oxide. So I'm going to put grams of iron 3 oxide and grams of iron in the bottom. So the units work out. And I'm demonstrating here we can do this without figuring out what the chemical formula is. So from my percentage, I have 69.94 grams of iron, so that's going to go in the denominator, and 100 grams of iron in the numerator. In a percentage like this percentage has 4 significant figures. The 4 significant figures are in the grams of iron. That's per exactly 100 grams of the iron 3 oxide. So this 100 here would be considered an exact number. So just overlook it when you're doing sig figs. So we've got 58.7 times 100 divided by 69.94. And I'm getting 83.929. And some other digits. My starting number had 3 significant figures. That's what my ending number is going to have. Then I rounded 83.9 grams of iron 3 oxide. Always a good idea to ask yourself, is it a reasonable answer? So if I have 58 grams of iron, should the mass of the whole compound be larger or smaller than 58? It's got to be larger, right? Because there's iron and oxygen, so the mass of the compound has to be bigger. And this mass is bigger. The common error is to get your conversion factor upside down, which makes the number smaller, and then you can see, oh, wait a minute, there's no way that the compound can be smaller. It'd be like having a class of 15 boys where there's a total of 12 children. Doesn't work, right? Question?
So, when you put it in the compound order, are you just doing it like how it is? So 58.7, 4.7, never mind.
Yeah. Yeah, you know, it's like with email addresses, these little tiny details. You know, the decimal point in the wrong place, the answer comes out wrong. But always ask questions, okay? Anybody else have any questions? We can also get conversion factors directly from the chemical formulas without using percentages, because the chemical formulas show us the relationships in terms of numbers of particles. So we look at the formula for that Freon 112, C2Cl4F2. The formula itself tells us there are 2 carbon atoms in 1 molecule of this. So there are 2 moles of carbon in 1 mole of the compound. Just like if you have 2 bicycles have 4 wheels, right? How many wheels would you have with 2 dozen bicycles? 4 dozen wheels, right? You just change the unit, the numbers stay the same. So we can do this in terms of atoms and molecules, or moles of atoms and moles of molecules. We can also look at this and say, well, there's 4 moles of chlorine in 1 mole of the compound. Okay? So the chemical formulas give us the relationships between compound and element, but very important, it's in moles, not in mass or grams. So we can't say that there's 4 grams of chlorine in 1 gram of the compound. It doesn't work. Moles are counting units. So determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. Well, let's write down the number. Let's not use the highlighter. 7.2 grams of oxygen. No, that's not oxygen. I'm trying to find oxygen. Wake up. That's aluminum sulfate. Okay, I'm trying to find grams of oxygen. I don't have a percent composition. So what I need is the chemical formula for aluminum sulfate. So I'm going to do that down here at the bottom. What kind of a compound is this? Ionic, molecular, or an acid? It's ionic. So the first word, aluminum, talks about the first element. Aluminum's a metal, right? So if it starts with a metal, it's ionic. So that means we need to look at the ions with their charges so we can figure out the formula. So I've got aluminum, and what's the charge on aluminum? 3+, because it's in group 3A. And then sulfate. So 4, 2-. Got to memorize that one. If you're shaky on those, give it your best guess and then look it up. So here I've got a +3 and a -2, and I need to put those together so that they're going to add up to 0. So I'm going to need 2 of the aluminums and 3 of the sulfates. So aluminum 2, SO4 3. Because I have multiples of a polyatomic ion, I need to put parentheses around it because I don't want it to look like I've got 43 oxygens. So this gives me the relationship between number of oxygen atoms and number of molecules, or moles of oxygen and moles of molecules. So looking at that formula, I'm going to do 1 mole of the compound, and I'm interested in how many moles of oxygen are in that. How many moles of oxygen in 1 mole of aluminum sulfate? 12. Because in 1 formula unit, or call it a molecule, it's not really a molecule. In 1 formula unit here, you're going to have 3 of these sulfate ions. Each of them has 4 oxygens. 3 times 4 is 12. Okay? So this conversion factor comes from the chemical formula. But that's relating moles. It's not relating grams. Here I've got grams, and there I've got grams. If you're ever stumped about what goes in the middle, try moles. Moles in the middle. It reminds me of that old TV show, Malcolm in the Middle. It's moles in the middle. We'll find that moles often ends up in the middle of our calculations. So we could go from grams of aluminum sulfate to moles of aluminum sulfate. And I didn't leave enough space, so I'm just going to erase that and move it over. Trying to get to grams of oxygen over here. So I can go from grams to moles of the same thing using the molar mass. Okay. And now I just came up with this relationship between moles of oxygen and moles of the compound. So I can go to moles of oxygen. And then using the molar mass of oxygen, I can go from moles to grams. Are you beginning to see the usefulness of dimensional analysis? If you can put the units together, this is so much simpler, and it doesn't require very much thinking. So if you're still shaky on dimensional analysis, ask me lots of questions during lab, because you're all capable of getting it. And once you get it, you'll be so excited, because it just makes everything easier. So I've got my path. That's the hard part. I have 3 arrows in my path, so that means I have 3 fractions in my equation. So I start with 7.2 grams of aluminum sulfate times in a line, times in line, times in line. The units in my path are the units in the numerator. Grams of aluminum sulfate to moles of aluminum sulfate. I don't always leave myself enough room. It's okay. And then to moles of oxygen and grams of oxygen. Then I fill the denominator units in so they cancel out. cancel. We've got moles of oxygen and moles of aluminum sulfate, and so we have to specify. We can't just say moles, because then we'll not know moles of what. Now I put the units in. No, those were the units. Now that I have put the units in, I put the numbers in. So this was our relationship that we got from the chemical formula. So that's this one in the middle, the mole to mole business. So there's 12 moles of oxygen and 1 mole of the compound. Grams to mole, moles to grams, always the molar mass. Look at the periodic table. A question?
Where did the 12 come from?
The 12 came from down here, where I'm looking at this formula, and in one of these units, 4 times 3, 12 oxygens. We could also do, sulfur or aluminum, but the question is asking for oxygen. So I like to leave the icky ones for the end, and that one's, This one's easy. What's the mass of 1 mole of oxygen? 16. So 1 mole is going to be 16.00 grams, or 15.9994. And now I have to calculate this. That's probably correct, but I have to work it out myself. And then I'll ask you if you got the same. So I didn't really leave much room down here. I'll squeeze it in over here. So aluminums. I have 2 aluminums times the mass of aluminum. And I have 3 sulfurs times the mass of sulfur. Oops, and 12 oxygens. The decimal point there. Sulfur's is 32.10. Well, yeah. What is wrong with my head? It's 07. I'm thinking something else. Okay, let's fix that. $342.17. Is that what you got?
1.4, but my decimal on sulfur's different.
Yeah. So 342.17, give or take, in the last couple digits. So I would say that has 4 significant figures. But look, we're starting with 2. So 4, 5, 6, it's not really going to matter very much. But you want at least 4. So there's my molar mass. I stick that in here, 342.1. If it bothers you that there's no number on the top, that would be 1. 1 mole of that compound weighs 342.17 grams. Any questions? Now we just run it through the calculator. And I think the best way is to start at the left. 7.2 times the top, divide by the bottom, times the top, divide by the bottom, times the top, divide by the bottom. And of course, if you're multiplying or dividing by ones, you're welcome to skip those. But if that bothers you, you're welcome to punch them in as well. 342.17 times 12 times 16. So I'm getting an answer here which would have 2 significant figures of 4.040 grams. That would round to 4.0 grams. Yes?
So I got the same answer, but on the last conversion practice, I did, I did the grams of 12 moles of oxygen over 12 moles of oxygen. But it would be the same.
That would be the same thing. But so there, what you're doing is you're multiplying the top and bottom by 12. Those are going to cancel out. It just gives you more opportunity for mistakes in the calculator. So it's not wrong, but I don't think it's the ideal way. Because, we're looking at this and saying, well, there's 12 oxygens. Well, that's true, but we're taking care of that in the mole thing here. So here we're figuring out there's 12 moles. Now we just want to know, well, what's the mass of 1 mole? And we're multiplying it by the number. Any other questions? Did that round off the same as yours then? Yeah.